Okay, in this lecture, we review the QPSK modulation scheme. In the last lecture, we covered QPSK and its different variants. You know that the QPSK data is divided into two bit streams. One is even bits and the other is odd bits. And these are modulated by in-phase component, and the odd bits are modulated by quadrature phase component. So the overall signal is of the form 1 by under root 2 di of t cos of 2 pi f naught t plus pi by 4, and similarly we have the quadrature component. So we can have the numeric values of these in-phase component, right? And we have the numeric values of the quadrature phase component. And depending on these in-phase and quadrature phase component, we can generate a carrier with cos 2 pi f naught t plus theta of t. And this theta of t is in fact is the phase of the modulated signal. So QPSK waveform is in fact is represented by a baseband signal with positive and negative voltage levels, and we represent the random data stream with 1 and zeros with positive and negative voltage levels. For example, we have 1 1 0 0 0 1 1 1 here. So this is the random data stream. So in BPSK, what we are doing, we are representing these by positive and negative cosine of omega ct. But here we have the positive and negative sine of omega ct component, which is the quadrature component. So this is in fact is the BPSK part which is in phase, and the BPSK part which is quadrature phase. So the QPSK is divided by two BPSK streams, one in phase and the other is quadrature phase. So after parallel conversion, so the symbol duration or the bit duration is spans from 0 to 2t, and similarly for the quadrature phase component, and this is the modulator for in-phase data bits, for the even data bits and the odd data bits, and this is the generated carrier. So this is the example that the signal is in fact is represented by in-phase and quadrature phase component. So the in-phase component is x of t, and the quadrature phase component is y of t, and this is in fact is the carrier component. So when we want to take the real of this, so this would be in fact x of t cos of omega naught t minus y of t sine of omega naught t. So we take an example of the quadrature implementation of the modulator. So in this x of k is 0.707 of the amplitude value, and y of k is 0.707 of the amplitude value. When we take the complex envelope representation of the signal, so we will take it as g of k ej omega naught t, and the quadrature implementation of the modulator is in fact is this G of K and this carrier component. So simply these are the numeric values which multiplied by the in phase carrier and the quadrature phase carrier. So here we have the value of 0.707A and minus 0.707A. So if the voltage levels assigned for the bit is 1, so it is simply 0.707 and minus 0.707. And mm, when you multiply it in magnitude and phase component, the generated carrier has a phase offset of pi by 4. So we can look this in the diagram. The last time I showed you that I missed this diagram. So this is in fact is the 0.707A amplitude of the carrier component, which is A sine omega naught t. So this is in fact is the carrier component which is leading pi by 2 and have the amplitude of 0.707 omega naught t plus pi by 2. So I just some and notes that this lag part is representing by this cosine omega naught t minus pi by 2, and this is in fact is a sine omega naught t, and this leading component is in fact is this leading component is in fact is this and this is 0.707A cosine omega naught t plus pi by 2. This is the leading component of the signal. So when we add up these two signals, which is 0.707 A sine omega naught t and minus 0.707 A sine omega naught t. So the reference signal is in fact is 0.707. The summation of these two signals is this signal. So this is in fact is the summation of these two signals. So to check the lead and lag, so we can consider this dotted signal as the reference signal, and this is in fact is the lag, and this is in fact is the lead component. So in short, we can say that we can modulate the QPSK signal with quadrature implementation. So here x of k and y of k are the numeric values assigned to this carriers for modulated symbol. So as far as the bit error probability is concerned, so BPSK and QPSK have the same error probability, because if you see the EB by naught to SNR relationship, so it would be like this, that the signal is divided by 2 bits and the data rate is also divided by 2 bits, and finally EB by naught have the same relationship we have for PPSK signal. So also last time we discussed the gray coding scheme. So in gray coding scheme, we increase the decision boundaries of the detected symbols. In that way, we reduce the probability of bit error. So this is in fact is the gray coded scheme in which every adjacent bit uh, uh, is just a change of 1 bit, because if we go from S0 to S1, we have 1 bit change, and we go S0 to S3, we have 1 bit change. And similarly, if we move from 11 to 10, 11 to 01, to the same, there is a 1 bit change. So this gray coding has an advantage and no disadvantage. It reduces the probability of bit error rate. Now there is another question that we have discussed the different variants of QPSK, which is offset and staggered QPSK and pi by 4 QPSK. In these modulation schemes, we have discussed uh, we have discussed we have discussed that we have no 180-degree phase shift in offset QPSK, and in pi by 4 QPSK, we have no zero crossing. So that is the advantage. But there are still fluctuation in the envelope. So the received envelope still have fluctuation, which is not suitable for non-linear power amplifiers used in satellite communication. So also we want to have the non-coherent detection of PSK. So this is in fact is the differentially encoded PSK scheme. I will come to the point of non-constant envelope changes can be overcome by MSK modulation schemes, which is continuous phase modulation scheme. And but at the moment, I go to the differential part of PSK, which is the non-coherent version, because all these variants of QPSK needs a phase information at the receiver. But there is no other way of non-coherent detection. Instead, we differentially encode the signal and then transmit it, and then we decode it. So first we go to the orthogonal signaling. That orthogonal signaling is just like have the probability of bit error rate is equal to m by 2 divided by m minus 1. For this, we can see that the probability of bit error at the least significant position is say that if we have uh, detected this bit in error or this symbol in error. So the probability of error is in fact is m minus 1 symbols are detected correctly. And so out of 8 symbols, we have 7 symbols are detected correctly. What about the probability of bit error if we have 8 symbols and we have 0 detected instead of 1? So it means there are chances of this, and this. So it is in fact is 4 by 7. There are 4 by 7 probability. So because the half bits are in 0th position and half bits are at 1 position. So this is in fact is 8 by 2, which is 4. So the ratio of this is 4 by 7, and that is probably 1 by 2 if we increase the value of k. So here we also implement the gray coding, because if we don't apply the gray coding, so the distance is non-uniform in PSK. So this is the example of 8 PSK. So if we don't apply the gray coding, so this distance is non-uniform, and when we apply the gray coding, the distance is uniform. So the differential version of PSK, we first use the binary PSK and how we detect this. So first of all, we have the exclusive NOR operation. The exclusive NOR operation is between the current bit and the previous decoded bit. So that would be in fact is the current decoded bit, and for the similar bits it has 1, and for the dissimilar bits it is 0. So we have this exclusive NOR operation. So we have this current A by K with the previous bit, and then we have the exclusive NOR, which is 1, and similarly we have this decoding operation, and then we have the exclusive NOR 1, and then we have 0 and 1, and we have 0. Now this decoded bit is in fact is modulated by phase information. So for 1 we are using the 0 phase, and for 0 we are using the pi phase. So this is in fact is the encoding of phase. So what about the receiving side? At the receiving side, we have the exclusive NOR with the previously received bits. So we have the estimation of the bits. So we have the exclusive NOR of the previous bit and the current bit, and that value is 1. And then we again have the exclusive NOR of this, and we have 1. And then we have 1, 0, and we have 0 here. So this is the exclusive NOR operation for the estimated bit. Advantages: the phase ambiguity can be resolved. Non-coherent detection techniques can be used in that way. And later on, we can see the demodulator, and we can see that how can we utilize these two advantages. So, for example, if the bit stream is inverted, for example, in that case, there will be no error in detection. So if we have the received bit all inverted, so we all have the same estimated bit stream. But the problem and disadvantage is that because it is based on the previous bit for decoding, so if there is one bit error, so it leads in the estimation of 2-bit error. So the estimated bit errors are 2 in numbers. If we have one erroneously received bit, so here erroneously 1 comes, and this one is in fact cause these 2 bits of error. So the encoded sequence DK is used for the phase shift of carrier for 0 for 1 and pi for 0. So this is how you can see that the modulated differentially encoded BPSK scheme. So how we can detect it, that the decoded bit stream is delayed by a version, a delay by a symbol duration, and we have the exclusive NOR operation to have the estimated error, as we have seen in the previous slide. So there is a sub-optimum detector and optimum detector. In the sub-optimum detector, we just based on the previous case, we delay the bit and we integrate it for the symbol duration, and then we sample it, and then we go to the decision stage. But in this case, first we optimum detector, first we integrate the bit over the symbol duration, and we delay it, and then we exclusive OR it. And similarly, for the quadrature branch, we do it, and then we sum up the signal, and then we sample it, and then we take the estimate. So this is the optimum detector for the differentially encoded binary PSK. So the probability of bit error can be calculated, but first I showed you here that, for example, there are 2 bits. So one bit is modulated by cos of omega naught t plus phi, which is you know that the 1 bit, and the 0 bit is modulated by plus minus phi. So because plus minus phi is one or the same thing, so it is represented by 0. So this is 1 and this is 0. So the symbol is of 2-bit duration, because in fact either we have the possibility that we have 1 1 and we have uh, 0 0, and we have uh, 1 0 or 0 1. So this symbol duration is 2t, because the symbol is based for 2-bit data, and it depends on the previous bit to be decoded. So the implementation of this is understood by that the for a 2-bit duration, these 2 symbols are orthogonal. And how can you check this? That it can be checked that if you have the cross correlation of symbol 1 with this, or in this form you have the cross correlation with this, so the answer will be 0. So that value will be 0. So for 2t duration, they are orthogonal to each other. So we are the match filter. These match filters match the received signal for S1 of t and S2 of t. So these two branches is for S1, and these two branches for S2. So what we will have, if the received signal match with this one and this one, so you will have the sum here is 2e, right? It's 2e. And here the output is 0 if the received symbol is S1, and vice versa in the case of S2. So by a close observation, we can reduce the number of match filters by having only two branches. So we have the correlation here. Here the correlation is E if S1 is transmitted, and here the correlation is 0 if S1 is transmitted, and even then we decide the correct symbol. So this is an example of differentially encoded 8 PSK. So in this we have the 3 input bit stream, which is encoded into I and Q phases, and then we have pulse shifting, and then we modulate and some of the signal. So data encoding is in that way that the delta phi of k is 0 for first symbol pi by 4, and for 100 for 7 pi by 4. So they are in fact gray encoded. These are in fact are gray encoded data, and these are the phase difference between the adjacent symbols. So if we have the input data of 110, so we just check here 110 is pi. So we put it pi here, and 0, similarly we check the table, and 001 pi by 4, and 110 pi, and 010 is 3 pi by 4. But how we calculate the phi k? Phi k is in fact is phi k minus 1 plus delta phi k. So we take phi k minus 1 is initially 0. So we can sum up delta phi k, which is pi, and this is in fact is pi. So then we have sum up, this is phi k minus 1, this is phi k minus 1, and this is delta phi k. We sum up these two, and we will get the result of this. And similarly, we sum up these two to get the result of this. So this is in fact is